All right, ideal gas law calculations. Okay, so this is taking the gas laws to another level. Earlier in the year, you've already done Boyle's law, Charles' law, Gay-Lussac's law. You did a little bit of review with that. Now we've been working on, or will work on, Avogadro's principle and how it connects to the ideal gas law. Okay? So again, we wanted to take the gas laws one step further, especially since, our classes this year have done such a phenomenal job with all the other material, and now we have some time to kind of scratch the surface on this. I mean, obviously I'd like to spend more time on it. Maybe in future years we will. It just depends on the classes. But again, we might as well take this to another level to continue to enhance your preparation for the high school. All right. So I'm going to do a couple word problems, and I want you to notice up here, these are big. These little unitary ratios up here are going to be big. We know how to work through unitary ratios, but I will tell you this. The R value that I'm going to talk about is going to be really important. That unit is actually there to help you, and I'll talk about that in a second. So let's take a look at this first problem. It says a tank contains 105 moles, you know about the mole concept, of chlorine gas. Now let's pause for a minute. Do they mean chlorine atoms, or do they mean diatomic chlorine? Well, think about it. Would you want chlorine atoms, which are a halogen, run around in a tank unstable? No, that would not be good. So the chlorine gas that we're talking about is diatomic. Remember the Brinkelhoff principle? Again, two chlorine atoms want to share a pair of valence electrons, right, to get that full atom shell to be stable. So overall, we're talking about 105 moles of Cl2, diatomic chlorine. Now think about that number for a minute, 105 moles. Well, how many Cl2s is that in the beaker? So it's 105 times 6.02 times 10 to the 23rd, which you know is an enormous number. Now, if you think it's 10 to the 40th, you better go back and watch the mole calculation video. Okay? But again, it's a pretty substantial number. So the other given, so we're going to write down this given, that's N, number, quantity, moles. 105 moles of Cl2. So you list that. Now again, it's almost like we're going back to the format of the first half of the year. Because again, in chemistry, it's givens, formula, plug in, answer. Whereas physics, it's free body, this formula. It's much more, not complicated. It's just many more calculations within one. These are pretty straightforward. Pressure, 54 atmospheres. And I'm going to want you guys to give me pressure and use atmospheres for pressure, okay, in all these problems. I also want you guys to be able to use use Kelvin, okay, in our problems, but we're given Celsius, and we have to calculate the volume of the tank. Okay. But the given here, though, that we're going to use, the standard, or this constant R value, is going to be 0.0821. Now, here's the nice part about this unit. Even though it looks complicated, I'm going to talk about it for 1 second, because units are important. Atmospheres times liters over moles times Kelvin. The nice part about this unit is it almost acts as a reminder. Your final answer, right, we should get using atmospheres, liters, moles, Kelvin. So by looking at this unit, it almost acts as a reminder. Well, if I give you volume, right, which would be which I could in milliliters, you're going to have to convert it to liters. Now, will I do that? Well, you know me pretty well. Of course I will. You know me. The more dimensional analysis practice you have, the better. What if I give you a pressure in torr, or PSI? Well, you're going to know to convert. Let's take it one step further. You ready for this? What if I gave you mass? What are you going to do with mass? What if I give you the mass of a sample? What are you going to do? Oh! Mole calculation. Again, everything builds. So this right here is a really helpful unit to remind you, okay, and it goes back to this. Here's what I have. That's what I need. Let me take inventory when I list my givens neatly and systematically to make sure I have everything I need so I know where to go. Okay? This is why you are expected to continue to show your work in a systematic format, because there's so many little conversions you're going to need to do. And if you do this and you think the problem, not just do it, think and do it, it's almost impossible to make a mistake, and you understand it better. Okay, that's why we make you show the work like this. Okay, so you have your given, so we have a formula. It's very simple. PV equals nRT, right? And you need to solve for V. Easy. Divide P on both sides of the equation, just like that. That cancels out. Now you're given V equals nRT over P. Okay, so that's our formula. Now we're going to plug it in. So V is what we're solving for. So N, we've got 105 moles of Cl2 times R 0.0821 atmospheres per times liter over mole times Kelvin times temperature. Look here. I need Kelvin. I've got Celsius. See the beauty of that unit? I need to add 273 to that. And when I add 273, all you have to do is show that right here. You, as a result, will have 318 Kelvin. So you're going to plug in over here 318 Kelvin divided by our pressure, which is totally appropriate, atmospheres, 54 atmospheres. Your final volume will be approximately 50.7 liters, okay, diatomic chlorine. So you need to make sure your formula is correct and make sure it's shown properly. So again, these calculations are very simple, but you really need to take inventory of your units. Make sure you do all necessary conversions before you follow through with the answer. Let me just look through the lens real quick and make sure that all came through so I don't keep doing problems and you can't see them. And that's pretty good. Let me move it over a little bit. Okay, that's good enough. Okay, good. All right, let's do another one. Let's take a look at, let's go down to number 4. Let's take a look at number 4. So just flip the page, go to 4. I'm going to erase this. So number 4, these oranges. Okay. A tank of oxygen has a volume of 1,650 liters. The temperature of the gas inside is 35 Celsius. If there are 9,750 moles of oxygen in the tank, what is the pressure in PSI? Okay, so let's take a minute here. Let's look at what we have. We have a volume of 1,650 liters. First step. Temperature inside, 35 degrees Celsius. Okay? Now, something should be going on with your head about that. Wow, 9,750 moles of oxygen in the tank. Review of chemistry, prior knowledge. Are they oxygen atoms or are they diatomic oxygen? They are diatomic oxygen. Again, that means you've got 9,750 moles of these, which means 9,750 times 6.02 times 10 to the 23rd of those. That's how many you have. That's a lot, okay? So that's a lot of gas you got right there. That was funny. Okay, and what else? Oh, our given. And watch this now. We're going to keep the standard. 0.0821 atmospheres times liters over mole times Kelvin. Okay. So let's start off. We need to get pressure, but we got to get it in PSI. Now, again, go down here as your reminder. Okay? We're solving for pressure. Now, what we can do is this. Liters looks good. This is fine. Celsius, no. We need to convert to Kelvin, add 273, so you're given, what is it, 308 Kelvin. Moles are fine, but what about this PSI? So here's what we can do. Let's solve for this problem, and let's put it in atmospheres. Let's go for atmospheres first. And then once we have a final pressure with atmospheres, then we can convert to PSI with a simple dimensional analysis calculation. So let's set up the equation. So it's PV equals nRT. We need to isolate P on the left side of the equation. So we just quickly divide by V on both sides, cancel out the V. You're left with P equals nRT over V. Okay? So now everything looks good. Our units all line up. They're all appropriate. Plug it into the third box. P equals 9,750 moles, right, of what? Oxygen gas. And I want you to write O2, and I want that up there too. Because it's just good reminder, good nomenclature, good conceptual reminder of diatomic oxygen gas times the constant, 0.0821. I'm running out of room. Atmosphere liter times mole times Kelvin times, what do we got, temperature? 308, you got to believe me if you can't see it, Kelvin. Okay, I don't know if you can see that, but it's 308 Kelvin. Over 1,650 liters. Okay, so now down here in your third box, you can give me a final answer after calculating that. Hopefully I didn't make a mistake on the calculator. I got about 149.4 atmospheres. Now, you need to go back and look at your givens. And you wrote a little note. You need this answer in PSI, pounds per square inch. You now have atmospheres, and that's okay. But we need to convert. So, in the year 2019, the class of 2018 and 2019 in Challenge Science. Now, future classes that are watching this, you're more than likely going to have to memorize all these, okay? Because this class is doing this for the first time. So you can thank this year's class for helping you people in the future learn more, okay? It's almost like this class is paying it forward. They also paid it forward with momentum. Good job, 2018, 2019 Challenge Science people. Okay, so now, this is our given. So when you look on the other side, you see that 1 atmosphere is equal to 14.7 psi. So how do we do that? We show dimensional analysis. We show it appropriately. So right here I have atmospheres up here in the numerator. I need atmospheres in the denominator to cancel out those units. I need to get psi. Okay? So what are the numbers with a unitary ratio? It's 1 atmosphere to 14.7 psi. Cancel, cancel, multiply those two. Your pressure in psi should be, what is it? I have it written down. About, if my calculator's right, 2196 psi is your final answer. Okay? Again, it's a very easy calculation, but being organized and showing that systematic approach, being very clear with your units, allows you to get the problem correct. Okay? So again, even though you had a final answer here, you still have to use that dimensional analysis component to get that final answer. Okay? Let's do number 6, and then you can do the rest on your own. So I'm going to erase this. I hope you can see it well. It's really not hard. Okay, here we go. Last one. Let's take a look at this one. Calculate the volume of a CO2 cartridge. Now, cartridge isn't that large. This isn't some huge tank. So obviously we should have a lower quantity of gas in here. So the volume of a CO2 cartridge, you have to calculate the volume. So I'm going to put a question mark there. And obviously you need to know you have to have it in liters. Something liters. Has a pressure, oh boy, of 850 psi. Uh-oh. And the temperature is 21 Celsius. The cartridge contains 0.273 moles of CO2. Okay? So ultimately, we know what a Lewis structure of CO2 is like. We know it's a nonpolar molecule with 2 slightly polar bonds. We know it exists as a gas room temperature because these IMFs that may develop between them are very weak. See all that review? That's why it's found at a gas room temperature. But here's my thing though. You're given this, you're given your R value, and I want in atmospheres. So your value down here, don't forget this, 0.0821 atmospheres, liters, over mole times Kelvin. Okay, So now, instead of showing that extra dimensional analysis step at the end, now it seems like to get volume in liters, I need to show my dimensional analysis here at the beginning and do a simple conversion here at the beginning to get the Kelvin and to get this to atmosphere. So real quick, I'm going to erase that Lewis structure up here. Right here, I'm going to add 273 to convert to Kelvin. That would become, what's that, 294? Then I would do this. Make the box a little bit larger. PSI goes to the bottom. Atmosphere is up top. What's the unitary ratio between them? We know it's 1 atmosphere to 14.7 psi. Cancel both out. You're left with 850 divided by 14.7. 850 divided by 14.7 gives you, so there's the work right there. So it's going to be 57.8 atmospheres. Okay, so now, make sure I got room. All right, so you have big, so now take inventory of your givens. We got atmospheres. We're going to get liters. We got moles. We got Kelvin. Now we may proceed with the problem. Write down your formula, PV equals nRT. Again, we're isolating V, we're solving for V. So we need to solve for P on both sides of the equation. Divide that, oh my gosh, my voice cracked. Divide that out, you're left with V equals nRT over P as your formula. Now we're going to plug in, I'm going to try to write this a little bit smaller. V equals N is 0.273 mole. Now real quick, 0.273. So when you multiply that by 6.02 times 10 to the 23rd, would you expect it to be greater than 1 mole or less than 1 mole? Obviously it's less than 1 mole. It's about 27% of a mole. Okay? So your value of actual molecules of CO2 gas in there is going to be less than 6.02 times 10 to the 23rd. Okay? Always try to think the problem. Use what you've learned at this point of the year in May, June. You know so much. Okay? Always apply what you learn because everything builds. You now know that now. Now that you're exactly how you should be working. Perfect. Okay, what else we got? R, the constant. I'm running out of room. 0.0821. And I'm only going to put the first letter because I'm running out of room. Atmospheres times liters times mole times K times, what else we got there? T of 294 Kelvin. I wrote on the wall. Probably can't see it, but I promise I put a unit there because every number's got a unit in this case. Divided by P, which is 57.8 atmospheres. So in case you can't see it, it's 0.273 moles of carbon dioxide. Our constant of 0.0821 atmospheres times liters over moles per Kelvin times 294 Kelvin divided by 57.8. Your final answer is going to be about 0.305 liters. Now let's think for a minute here. Think the problem when you check it. It's not just, oh, let me plug this in, make sure I put it in the calculator right. Let's think for a minute. First off, it said cartridge. Cartridge is not a huge tank. Cartridge is small, okay? So you know, if you think soda, like a soda bottle, right? You think about a 2-liter bottle of soda, you can visualize what that looks like in terms of volume. You know what a 1-liter soda bottle looks like. Half of that, smaller, okay? Well, given a cartridge of gas, and keep in mind the temperature, you know, isn't too high, okay? It's not that high at all, right? We know they have weak IMS, we know they're moving around, we know that we have significantly less than 1 mole. I wouldn't expect the volume to be that high. Well, would you consider 0.305 liters to be high? Think about it. Oh, visualize a 2-liter soda bottle. Now visualize a 1-liter soda bottle. Take that 1-liter soda bottle and think about what 30% of that volume would look like. Does that answer make sense with your givens? Absolutely. Okay? So again, try to think the problem. The more you think, the more you'll understand, the more comfortable you'll be, the less stressed you'll be on the exam. Okay, that's that. I hope these work out well for you. Again, for this 2018-2019 class, thank you for taking on this work because you know what? It's a weakness in honors chemistry. I hope we've helped a little bit with that. And I'm hoping that this will help kids that take challenge science down the road. Again, great job. Get to it. Get the work done. All right, that's it. We'll do a few in class.